Okay, so this problem can be solved in two ways. We're not going to discuss a lot these two options. So one is straightforward. You just put a point like source, electric dipole source in CST, and you calculate power that is emitted to different channels. Another option, another approach is simpler. Actually, you only need to calculate the modes of the waveguide, and that's it. From these simulations, you can find what is the power that will be channeled to this particular waveguide modes. So there are some like limits to these approaches. So we're not going to discuss it a lot. So basically, first two steps is the first option, where we calculate only the eigenmodes and then do some post-processing to find the power emitted to these modes. And the third step is we just add a point like dipole, and that's it. So do it straightforwardly. So let's start with the first option. So for the first option, we need to calculate eigenmodes of the waveguide. So we don't put the source near the waveguide, we're just considering waveguide itself. So in the previous class, yes, we considered also waveguide, the electric waveguide. In that case, we solved, so we found dispersion of the waveguide using eigenmode solver. Yes, so we use periodic boundary conditions in direction of the waveguide axis. In this case, we can use another option. So we know that the waveguide is homogeneous in x direction. So it's not periodic, so there is no real periodicity, it's homogeneous. In this case, we only need to consider a two-dimensional problem. Yeah. So you don't need to consider really 3D problem. You can do it like in COMSOL, use port. So port is a two-dimensional object. This is basically a cross-section of the waveguide, and then find the modes of this port. Yeah. So this is very similar to the numeric port of COMSOL. So the difference is that this particular port, this waveguide port that we will use, it has by default perfect electric conductor boundaries. So that means we can only find here the so we cannot consider radiated modes, leaky modes of the waveguide, only true waveguide modes. So we can use material absorption, that's fine. But if the waveguide's mode starts to leak, radiate outside of the waveguide, we cannot use this approach anymore. So let's start making the model. So let's consider first half of these settings that we need to set in our model. So the size of the waveguide radius 150 nanometers. So we're going to work approximately, if you take into account epsilon, so refractive index is equal to 4. So it's something close to 1 micron. So for units, we can choose, as usual, nanometers and terahertz, for instance. Type of solver. So which type of solver do we use for this particular problem? Do you know? Yes, there is one option is frequency domain. Another option is time domain. They are both, I think that to use frequency domain, we don't need to actually have, so we don't need to know what's going on in time domain, and we don't need a very broad spectrum. So just like, I don't know, 10 frequency samples will be enough for us. So in general. So I think the frequency domain is the best option. So in units, let's set nanometers and terahertz. And solver, as a solver, we're going to use frequency domain. So we are not using eigenmode solver, although we are going to find eigenmodes. We are not using eigenmode solver because we just want to find eigenmodes of this port. So it's similar to the COMSOL. When you have a numeric port, you don't use eigenmode solver, you use boundary mode analysis. So here, when you want to find modes of this port, you also don't need eigenmode solver. You use frequency domain solver, for instance, and there is an option to find eigenmodes of the port only. Okay, so we can use time domain solver and also find the eigenmodes of this waveguide port. But for instance, if you use time domain, you will have to use hexahedral mesh, and it's not the best option, especially since you have this curved object, cylinder, circle. So the tetrahedral mesh is usually the best in terms of accuracy and time of simulation. So frequency domain here is the best choice. Now frequency range. So just let's see once again. So our task is to calculate power emitted to the first two waveguide modes. So we're not going to consider many modes, just two first modes. Can you have estimate, a guess at least, approximately in which frequency range we need to work for these particular parameters of the waveguide? What do you
set modes of cylindrical waveguide? You can see it should be calculated by
the wavelengths compared to the rate.
It's the right direction of the thought, but you need to not just compare to the radius, but add something else. Not epsilon, but refractive index. And also, typically, it's not radius, but the linear size, which is diameter. And so, well, this will be just an estimate, yeah? Because if you remember something about the electric waveguides, so first modes, well, there are actually two degenerate modes, so we're not going to consider this this degeneracy. But anyway, so this first mode, it doesn't have cutoff frequency. So in principle, the fundamental mode is present at any frequencies. But so if you consider very low frequencies, this first fundamental mode, it's basically like a plane wave because it's very close to the light line. So it localized, but very, very poorly near the waveguide. So it's not very interesting regime typically. So you want to work in a regime where the wave is actually localized. And in this case, you really need to consider this estimate like diameter multiplied by refractive index. So 300 nanometers multiplied by 4, 1.2 microns. This is approximately the frequency where maybe first or second mode will appear. And they will be localized well. So 1.2 microns is approximately 250 terahertz. So you can take slightly higher value in order to be sure that you catch the second mode. And also you can take the lower bound. Well, in principle, you can take it much lower because you cannot be sure at which frequency the wave will be localized well, or like it's hard to tell. So it's just an estimate. But it's still good to have this in mind. So I already done this for you. So we're going to work in the range 180 to 280 terahertz. Actually, you can load the parameters from the file. Yeah, there are already these parameters. Actually, we will change it, but for now it's okay. So we have this fmin, fmax parameters, so we can set the frequency range. From fmin to fmax. Okay, so for materials, it's straightforward, just the electric with constant epsilon. Now geometrical objects, well, obviously we have a cylinder with given radius. What about the height of this cylinder, the length of this waveguide? How do we choose the length of the waveguide? What do you think? In our problem, it should be infinite, but in the model, it should be finite. So how do we choose this size?
By the wave.
So it should be equal to the wavelength. So much larger than the wavelengths. Why?
What's the wave? Transfer some distance. Because it shouldn't. Couldn't be any reflection.
Any? Okay, but why? Okay, maybe like some reflection, scattering, but does this depend on the size of the cylinder?
We play just modes of ports, so length is safe.
Yes. First, you need to understand what problem we're solving. We only want to find the modes of the port. So we're not going to excite this waveguide at all. We, for now at least, we just want to calculate the modes of the port. And in this case, that's true. The size of the cylinder, it won't matter at all. So you can take it arbitrary. And it actually doesn't matter because in the simulations, you're not going to solve the problem. I mean, the results, of course, will not depend, but the time of the simulation will also not depend on the size of the cylinder, because you will only solve the problem inside the waveguide port. The only thing that the size of the cylinder will affect is the time that the program will spend for building mesh. Because although you want to only consider the ports, the program will still have to build a mesh for the whole system. And if you take a very, very large cylinder, the program will spend maybe a few seconds to build this mesh. And if you take a very small cylinder, it will also build a mesh, but it will do this much faster. So the size doesn't matter. Actually, even if we wanted to excite this waveguide, yeah, the length of this cylinder, it wouldn't matter either. Because, so let's say we want to check the transmission through a waveguide. So we would put another port on the right side, and this port on the right side would absorb all propagating modes. So that means it doesn't matter where we place this port, at which distance from the first port, it doesn't matter, nothing depends on it. So maybe if you put it like at one mesh cell, maybe there could be some problem, but as soon as at least a few mesh cells, it won't be a problem. So you don't need to have something like much larger than wavelengths. In fact, the only time, like when we need to have size of some object much larger than the wavelengths, only if this object itself has actual size much larger than wavelengths. Yeah, so any boundary, any background distance, any size of this effectively infinite objects, it never much larger than the wavelengths. It could be lambda over 2, lambda over 4, even comparable with lambda, but not much larger. So that's why these simulations are efficient, because even if reality you have very large or infinite space claddings, in the simulation model, it's enough to have just lambda over 2, let's see. So we'll build very small cylinder for now. So what about background? Background properties. So what kind of distance we need to set? Zero in which direction? In all?
Just consider about both.
Yeah. So in X, well, yeah, in X you can use 0. That's not a problem. Yeah. Again, because you are only considered port actually, so it doesn't matter. So the simplest option is to make it 0. What about transverse YZ directions?
Yeah.
Yeah, so it's a little bit tricky. So there are two options. The first option, you build this model, so a cylinder bound calculation domain without a port first. And then you create the port which fills the whole plane, this YZ plane. So then the size of this waveguide port would be defined by this background distance that you chose. This is one option. Another option is you set the size of this waveguide port by yourself. And then the background distance would be the distance not from the cylinder to the boundary of calculation domain, but from this edge of the waveguide ports to the boundary of the calculation domain. So actually the questions here is what should be the size of this waveguide port, and should there be any distance between the waveguide port and the calculation domain boundaries? So what do you think about the size of the waveguide port?
Size. Great.
If you want to take in account that leaking modes, I think it should be bigger than cylinder.
So we cannot find leaky modes with this waveguide port because this waveguide, it's a hollow metallic waveguide with perfect electrical noun boundaries. So we cannot, using this waveguide port, we cannot find it. But you cannot take the size of the waveguide port equal to the diameter, because even if the modes are not leaky, just conventional waveguided modes, they still have evanescent tails.
Fine. Oh, of course, yeah.
So you need to take this into account. So you need depending on what is the size of these evanescent tails. Actually, the size of this waveguide port also should be maybe slightly different. So again, we want to consider the regime where these modes are more or less localized. So we're not going to consider the very low frequencies when the evanescent tails have like 3 wavelengths, let's say, size. So they're typically something around lambda over 4, lambda over 2. And so the size of the waveguide port should accordingly. So something around lambda over 4 typically is enough, maybe a slightly larger. And what about the distance between the port and the boundary of calculation domain? Do we need any distance here? So again, we are only considering a port. So we're not going to consider the whole problem. So it doesn't matter what happens outside of the port. So it doesn't matter. So the easiest way just to set it as 0 by default. Even if we wanted to excite this waveguide, yeah, we would still could set this background distance as 0. Because if we chosen the size of the waveguide port properly, then everything is fine. So this is the distance that we need. So let's change this setting. So let's go to materials and add dielectric. So let me check. Yeah, there is a variable named EPS. This is epsilon of the waveguide. And go to modeling tab, choose a cylinder. It's best if you orient the axis of the cylinder along x-axis as in the slide, because we're going to use some symmetry planes further just to avoid some differences. So choose orientation along x. So the radius, for the radius, we have variable r. And size will be from, so there is variable Lx, which is the size of the waveguide. So we can set it from minus Lx over 2 to plus Lx over 2. Background distance is 0 by default, so we don't need to change it. So background distance is 0 by default, so we don't need to change it. So let's go to boundaries. What do you think? What boundary conditions we should choose for this problem? Mm-hmm. Yeah, so if we choose open, then after we add waveguide port, the boundaries of the port will still be perfect electric conductor. The only thing we need to know that if we choose not open, but let's say magnetic, then the waveguide port coincides with the boundary of the simulation domain, so with this boundary. Then instead of perfect electric conductor, we would have perfect magnetic conductor, so they can be replaced. But they will be either perfect electric conductor or perfect magnetic conductor. For our purposes, it mostly doesn't matter, because we are considering only waveguide modes, assuming that the evanescent tails have decayed after, as soon as they reach boundary. So in principle, we can use electric, we can use magnetic, we can use open, even open at space. So again, doesn't matter, you can choose any of them. The only thing for X min, it's the boundary where you will put waveguide port. You have only option open, because if you put perfect electroconductor, the waveguide port will not work. So for X min, it should be open. All other boundaries don't really matter. So click OK. You can save also this project already. Let's check further. So we will not discuss the symmetry plane for a moment. We'll discuss it a bit later. Let's move further for now. So source of radiation. And so although we're looking for eigenmodes, we're not going to excite this whole system with any kind of source, but we're going to use waveguide port, which is usually a source of radiation. So waveguide port, to add the waveguide port, we go to ports, folder ports on the left, right click, new waveguide port. So put it normal to X, orientation positive, and by default, you see position full plane. So it just chooses this size of the waveguide port according to the size of the simulation domain. So instead of full plane, we will choose free and set here size of this port by ourselves. So we have variable L. So I think we're going to use this L. So we can set, for instance, for Y min minus R minus L. And for Y max, R plus L. And the same for Z direction. Maybe it's even too large, but okay, I think we're fine. What else? There is setting number of modes. By default, it's 1. So we need at least 2, and actually there could be more modes. So we just want to check that we are working in the range where we have 2 modes. So we will set it to variable n modes. So in the list of parameters, it's equal to 4. Just to be sure that we found the modes that we need. So n modes. There is also this option polarization angle. It could be useful actually for these cylindrical waveguide modes, because for some of the modes are degenerate, right? For instance, this fundamental mode, they're degenerate like a plane waves in free space. One of them is polarized, let's say, along y, one along z. But since we're going to use symmetry plane, so we don't need this option, because one of these modes will be filtered out by the symmetry plane. So for this particular case, we don't need it. So click OK, and now you have this waveguide mode. Let's go further. So source of radiation results. So what kind of results we need? So we always, for the waveguide, typically we need either eigenfrequency or wave vector for a particular frequency, or dispersion, dependence of omega over k. So of course, this eigenmode of the waveguide port will provide us with the wave number for a particular frequency, and we will make sweep over frequency and we'll get the dispersion. Also, field distributions will also be available. We will not change mesh. We'll just use the default one. So let's go to solver settings now. Let's open solver. So what do we have here? So the most important, it's the option calculate port modes only. So you need to check this. After you've done this, almost any other options do not matter. So just remove adaptive tetrahedral mesh refinement. And in principle, that's it. And click apply. So with this option, calculate port modes only, once you launch frequency domain solver, it will find only the modes of this particular waveguide port. And so it will find it. So it will find the wave number for particular frequency. So what is the frequency? The frequency is the central frequency of this global frequency range. So right now it will find the modes for the frequency 230 terahertz. And the problem is we want to change it. So that means that we have to change the global frequency range if we want to make sweep over the frequency. So we will do it in the following way. We have this variable f0. So right now it's 300. So this is the frequency for which we'll calculate waveguide modes. So we will set fmin f0 minus 1, and fmax will be equal f0 plus 1. So after you change it, click parametric update. Don't forget to click parametric update. So fmin is f0 minus 1, fmax is f0 plus 1. So once we set these particular limits of the global frequency range, the central frequency is now f0. So we can make sweep over f0 variable, and in this case, we'll get the dispersion. Okay.
There's no wave range for solar frequency.